universe is a tapestry of wonders and mysteries, and among the most profound is the question of its origin. Where did everything come from? And if the universe came from nothing, where did that nothing originate? This question isn't just scientific. It strikes at the heart of existence. From ancient myths to modern cosmology, humanity has always sought to comprehend the origins of the universe. Each culture and era has brought forth its own explanations, ranging from divine creation stories to scientific theories. However, the question of what precedes everything, or the notion of nothingness, remains an elusive and deeply philosophical challenge. As we embark on this journey to explore the origins of everything, we must first confront the enigmatic concept of nothing. This essay aims to guide you through this fascinating and often perplexing journey, shedding light on the most profound questions of existence and the universe. To understand the origins of the universe, one must consider the interplay between cosmology, philosophy, and theoretical physics. Cosmology provides a scientific framework for exploring how everything began, encompassing theories like the Big Bang and cosmic inflation. Philosophy addresses the fundamental nature of existence and reality, with thinkers like Leibniz and Kant posing questions that remain relevant today. These philosophical perspectives challenge us to think beyond empirical evidence and consider what it means for something, or nothing, to exist. Theoretical physics bridges the gap, using mathematical models and empirical data to explore the fundamental forces and particles that govern the universe. Quantum mechanics introduces the idea that on the smallest scales, particles can exist in states of superposition and entanglement, challenging our classical notions of reality. By considering the interplay between these fields, we gain a richer and more nuanced understanding of the universe's origins. The concept of nothing is a cornerstone of our exploration into the origins of the universe. In everyday usage, nothing might seem straightforward. It signifies the absence of anything. However, in physics, nothing is not a simple void. Even in the absence of matter and energy, the vacuum of space is teeming with quantum activity. Quantum mechanics reveals that particles and antiparticles can spontaneously emerge and annihilate each other in a vacuum, a phenomenon known as quantum fluctuations. This implies that even in what we perceive as nothing, there is a continuous dynamic process occurring at the quantum level. Philosophically, the concept of nothing has been a subject of deep contemplation and debate. Leibniz's famous question, "Why is there something rather than nothing?" encapsulates the existential dilemma. The scientific and philosophical investigations into nothing reveal a fascinating interplay between absence and potential. By exploring these concepts, we can begin to grasp the profound implications of nothing and its role in the origins of the universe. Curiosity is a fundamental driving force behind humanity's quest for knowledge. It compels us to ask questions, seek answers, and explore the unknown. From early astronomers to modern scientists, curiosity has been the catalyst for discovery. Each question answered often leads to new questions, creating an ever-expanding web of knowledge. Curiosity drives us to explore these mysteries, fueling scientific and philosophical inquiry. In our journey to understand the origins of everything, curiosity is our guiding light, leading us to new discoveries and deeper insights. By embracing curiosity, we can continue to push the boundaries of knowledge and uncover the mysteries of the universe. Section 5. Overview of the essay structure. To navigate the profound question of the universe's origin and the concept of nothing, this essay is structured to guide you through various perspectives and theories. The first section, Understanding Nothing, delves into the definition of nothing in everyday language and in physics. In the second section, The Big Bang Theory, we examine the most widely accepted explanation for the universe's origin. Next, Philosophical Perspectives offers insights from philosophers like Leibniz and Kant on the nature of existence and nothing. In Quantum Mechanics and the Origins of the Universe, we explore how quantum mechanics challenges our classical notions of reality. Finally, Theoretical models and speculations present speculative models such as the multiverse theory and the cyclic model. Together, these sections provide a comprehensive and nuanced exploration of the origins of everything, from nothing to the universe. Section 1. Nothing in everyday language. When we speak of nothing in our daily lives, we typically refer to the absence of things we can perceive with our senses. An empty room, a blank canvas, or a silent moment might all be described as nothing. However, this everyday understanding of nothing becomes problematic when we begin to explore the universe's origins. The nothing from which the universe arose was not merely the absence of matter or energy as we know them. It was a state that challenges our fundamental understanding of reality. To truly grasp the concept of nothing in the context of the universe's origin, we must venture beyond our everyday experiences and delve into the realm of physics. Section 2. The limits of intuition. Our intuition, while often helpful in navigating the familiar, can be a stumbling block when confronting the unfamiliar, especially in the realm of cosmology. We tend to project our everyday experiences onto the cosmos, expecting it to behave according to the rules we observe in our daily lives. However, the universe operates on scales and under conditions vastly different from our everyday experiences, rendering our intuition unreliable. To truly understand the origins of the universe, we must acknowledge the limitations of our intuition and rely on the tools of scientific inquiry. This involves formulating testable hypotheses, gathering observational data, and constructing mathematical models that describe the universe's behavior. Section 3. Nothing in classical physics. In classical physics, the realm of Newtonian mechanics and electromagnetism, nothing is often equated with a vacuum. This vacuum is envisioned as a completely empty space, devoid of any matter or energy. However, even within classical physics, the concept of a true vacuum, a region of space completely devoid of any fields or influences, is an idealization. The presence of gravitational fields, for instance, permeates all of space, even in the absence of matter. The advent of quantum mechanics in the early 20th century revolutionized our understanding of the vacuum and revealed that even in the absence of matter and energy as classical physics understood them, nothing is far from empty. Section 4. Quantum fields, a sea of potential. Quantum mechanics, the branch of physics that governs the behavior of matter and energy at the atomic and subatomic levels, radically alters our understanding of nothing. According to quantum theory, the vacuum of space is not an empty void, but a dynamic sea of quantum fields. These fields, unlike anything in classical physics, are fundamental entities that permeate all of space and time. Even in a region of space devoid of particles, the quantum fields themselves are subject to quantum fluctuations. This phenomenon, known as vacuum fluctuations, suggests that nothing is not static and empty, but rather a dynamic and energetic realm, a seething sea of potential where particles can flicker in and out of existence. Section 1. The Big Bang, a universe emerging. The Big Bang theory stands as the prevailing cosmological model for the universe's origin and evolution. It paints a picture of a universe vastly different from the one we observe today, beginning from a state of unimaginable density and temperature approximately 13.8 billion years ago. This primordial state, often referred to as a singularity, represents the limit of our current understanding of physics, a point where the known laws of physics break down. From this singularity, the universe embarked on a journey of expansion and cooling. As space expanded, energy densities decreased, leading to the formation of fundamental particles like quarks, electrons, and neutrinos. These particles, initially existing in a sea of radiation, interacted with each other at incredibly high energies, governed by the laws of particle physics. This early universe was a dynamic and chaotic environment, far from the relatively stable and structured cosmos we observe today. As the universe continued to expand and cool, these fundamental particles began to combine, forming protons and neutrons, the building blocks of atomic nuclei. This process, known as Big Bang nucleosynthesis, occurred within the first few minutes after the Big Bang and played a crucial role in determining the abundance of light elements in the universe. The Big Bang theory doesn't claim to explain the origin of the singularity itself, or what might have existed before it. It is a model that describes the evolution of the universe from a fraction of a second after the Big Bang onward, based on our current understanding of physics. However, the question of what caused the Big Bang, or what, if anything, preceded it, remains one of the most profound mysteries in cosmology. Section 2. Evidence for the Big Bang. The Big Bang theory is supported by a wealth of observational evidence. One compelling piece is the redshift of distant galaxies. This redshift indicates the universe is expanding. Another crucial piece is the abundance of light elements. The discovery of the cosmic microwave background radiation, or CMB, is direct evidence. The properties of the CMB align well with the Big Bang theory. Section 3. Cosmic inflation, a rapid expansion. The Big Bang theory leaves some questions unanswered, like the horizon problem. The CMB's temperature is incredibly uniform across the observable universe. Physicists proposed cosmic inflation, a period of exponential expansion. The universe expanded rapidly, driven by the inflaton field. This smoothed out initial inhomogeneities, explaining the CMB's uniformity. Inflation has gained support from cosmological observations, solving Big Bang puzzles. Section 4. The cosmic microwave background, an echo from the past. The cosmic microwave background radiation stands as one of the most profound discoveries in cosmology, providing a unique window into the early universe. It is a faint afterglow of the Big Bang, a thermal radiation that permeates all of space, carrying information about the universe's state when it was just 380,000 years old. Before this time, the universe was too hot and dense for atoms to form. Protons and electrons existed in a plasma state, constantly interacting with photons, preventing light from traveling freely. However, as the universe expanded and cooled, a crucial transition occurred. Electrons combined with protons to form neutral hydrogen atoms, a process known as recombination. This transition marked a turning point in the universe's history. With the formation of neutral atoms, photons were finally able to travel freely through space, decoupling from matter. These photons, carrying information about the conditions of the early universe, have been traveling unimpeded ever since, forming the CMB we observe today. The CMB's temperature, approximately 2.7 Kelvin, or minus 455 degrees Fahrenheit, is remarkably uniform across the sky. However, sensitive instruments have detected tiny temperature fluctuations in the CMB on the order of 1 part in 100,000. These fluctuations correspond to regions of slightly different densities in the early universe, the seeds of the large-scale structures we observe today. The CMB provides a wealth of information about the early universe, including its age, composition, and geometry. The detailed measurements of its temperature fluctuations have provided strong support for both the Big Bang theory and cosmic inflation, solidifying our understanding of the universe's early history. Section 5. The formation of structure from soup to galaxies. After the cosmic microwave background radiation, the universe entered the Dark Ages. The universe was filled with neutral hydrogen and helium gas, with no stars or galaxies. Tiny density fluctuations in the CMB shaped the universe. Gravity pulled matter together over vast distances. Higher density regions grew denser and hotter. Clumps of matter collapsed, igniting nuclear fusion, birthing the first stars. Massive stars exploded as supernovae, seeding heavier elements. These elements enriched the interstellar medium, forming new stars and galaxies. Smaller clumps merged, forming galaxies. Galaxies formed the cosmic web we observe today. Galaxies continue to evolve through mergers and collisions. The universe is a dynamic tapestry, shaped by gravity, matter, and energy. Section 6. The puzzle of dark matter and dark energy. The Big Bang Theory explains much, but puzzling discrepancies remain. Dark matter and dark energy dominate the universe's energy budget. Dark matter is invisible, but its gravity affects stars and galaxies. Galaxies rotate faster than expected, suggesting dark matter's presence. Dark energy accelerates the universe's expansion. This repulsive force counteracts gravity on cosmic scales. Dark matter and dark energy remain major mysteries in cosmology. Section 7. The limits of the Big Bang Theory. The Big Bang Theory describes the universe's evolution, but has limitations. It doesn't explain the origin of the Big Bang, dark matter, or dark energy. It relies on general relativity, which breaks down at high energies. We need a theory of quantum gravity to understand the universe's first moments. The Big Bang Theory doesn't address what existed before the Big Bang. Despite its limits, it remains our best model for the universe's history. Section 8. Beyond the Big Bang, the quest for a complete explanation. The Big Bang Theory marks the beginning of our quest to understand the universe's origins. It raises profound questions about what came before and the ultimate fate of the cosmos. Cosmologists explore ideas beyond the Big Bang, seeking a more complete explanation. These include string theory, loop quantum gravity, and multiverse scenarios. String theory proposes that tiny, vibrating strings are the universe's fundamental building blocks. These strings give rise to the different particles and forces we observe. String theory also suggests extraspatial dimensions, potentially unifying gravity with other forces. Loop quantum gravity proposes that space and time are made up of discrete chunks. This could resolve the Big Bang singularity problem. Multiverse scenarios propose our universe is one of many within a larger multiverse. These universes could have different physical laws explaining why ours is fine-tuned for life. The quest to understand the universe's origins is a journey without a final destination. Each discovery leads to new questions, pushing the boundaries of our knowledge. Section 1. Leibniz and the Principle of Sufficient Reason. The philosophical exploration of nothingness and the origin of the universe predates modern cosmology by centuries. Philosophers have long grappled with the fundamental question of why there is something rather than nothing, seeking answers in the realms of metaphysics and ontology. One such philosopher, Gottfried Wilhelm Leibniz, a 17th century polymath, approached this question with his principle of sufficient reason. Leibniz argued that for every fact, there must be a sufficient reason that explains why it is so and not otherwise. This principle, applied to the existence of the universe, leads to a profound question. What is the sufficient reason for the existence of the universe itself? If the universe arose from nothing, as modern cosmology suggests, what explains this emergence from nothingness? Leibniz, a devout theist, proposed that God serves as the ultimate sufficient reason for the universe's existence. In his view, God, being perfect and eternal, chose to create the universe as an act of free will. And this divine choice provides the ultimate explanation for why there is something rather than nothing. However, Leibniz's argument, while influential, does not satisfy all philosophical perspectives. It introduces the concept of a divine creator without explaining the origin or reason for the creator's existence. Additionally, from a purely logical standpoint, it is possible to question whether the principle of sufficient reason itself requires a further sufficient reason, leading to an infinite regress. Section 2. Kant and the Limits of Human Understanding. Immanuel Kant, an 18th century German philosopher, offered a different perspective on the concept of nothingness and the limits of human understanding. In his Critique of Pure Reason, Kant argued that our knowledge is limited by the structure of our minds, which impose categories of understanding on our experiences. These categories, such as space, time, and causality, shape how we perceive and comprehend the world around us. According to Kant, the concept of nothingness falls outside the realm of possible experience. We cannot have a direct experience of nothing because experience itself presupposes the existence of something to be experienced. Nothingness, in Kant's view, is not a positive concept but rather a negation, a lack of something that we can perceive or comprehend. Kant argued that when we try to apply our categories of understanding to the concept of nothingness, we inevitably run into contradictions. For example, if we think of nothingness as a kind of empty space, we are still presupposing the existence of space itself, which is a category of our understanding. This Kantian perspective suggests that the question of what came before the Big Bang, or what caused the universe to emerge from nothingness, might be ultimately unanswerable, at least within the framework of human reason. Our minds, bound by their inherent structure, may be ill-equipped to grasp the ultimate nature of reality or the concept of true nothingness. Section 3. The absurdity of existence. An existentialist perspective. Existentialist philosophers such as Jean-Paul Sartre and Albert Camus offered a different perspective on the question of existence and nothingness, focusing on the human experience of this seemingly absurd situation. Existentialism emphasizes individual freedom, responsibility, and the search for meaning in a world devoid of inherent purpose. From an existentialist perspective, the universe's existence is not a problem to be solved, but rather a reality to be confronted. The fact that we exist, that there is something rather than nothing, is seen as fundamentally absurd. There is no inherent reason for our existence, no grand plan or divine purpose. We are thrown into existence, as Sartre famously put it, abandoned to our own devices. This realization of absurdity can be both liberating and terrifying. On the one hand, it frees us from the constraints of predetermined meaning and allows us to create our own values and purpose. We are free to define ourselves through our actions and choices. On the other hand, this freedom comes with a heavy burden of responsibility. We are solely responsible for the meaning we create in our lives, and this realization can be daunting. The universe offers no guarantees, no safety net, and no ultimate answers. We are left to confront the void of nothingness and find meaning in the face of the absurd. Section 4. Nothingness as a catalyst for creation, Eastern philosophies. Eastern philosophical traditions such as Taoism and Buddhism offer a different perspective on the concept of nothingness and its relationship to existence. These traditions often view nothingness not as an empty void, but rather as a state of potentiality, a ground from which all things emerge and to which they eventually return. In Taoism, the Tao, often translated as the Way, is seen as the ultimate source of all things. The Tao is described as both being and non-being, encompassing both existence and nothingness. It is from the Tao that all things emerge and to which they eventually return, a continuous cycle of creation and dissolution. Buddhism, particularly Zen Buddhism, emphasizes the concept of shunyata, often translated as emptiness or voidness. Shunyata does not refer to absolute nothingness, but rather to the idea that all phenomena are impermanent and lacking inherent self or essence. This emptiness is not seen as a negative state, but rather as a state of openness and potentiality, a fertile ground for creation and transformation. These Eastern perspectives offer a different lens through which to view the universe's origin. Rather than seeking a cause or explanation for the emergence of something from nothing, these traditions often emphasize the interconnectedness of all things and the cyclical nature of existence. Nothingness, in this context, is not an absolute void, but rather a dynamic and creative principle, a wellspring from which all things arise and to which they eventually return. Section 5. The ongoing dialogue, science, philosophy, and the search for meaning. The exploration of the universe's origins highlights the ongoing dialogue between science and philosophy. These disciplines are intertwined in their pursuit of understanding reality and our place within it. From the Big Bang to the laws of physics, science unveils the cosmos. Philosophy grapples with existence, meaning, and knowledge. This dialogue is essential for understanding the universe and our place within it. In the early 20th century, a revolution swept through the world of physics, overturning classical notions of reality and ushering in a new era of understanding quantum mechanics. This revolutionary theory, developed to explain the behavior of matter and energy at the atomic and subatomic levels, challenged the deterministic worldview of classical physics and introduced a realm governed by probability, uncertainty, and the counterintuitive nature of the quantum world. Classical physics, with its emphasis on determinism and predictability, had painted a picture of a universe where the future unfolded inexorably from the present. Governed by immutable laws, quantum mechanics, in contrast, revealed a universe inherently uncertain at its most fundamental levels, where particles could exist in multiple states simultaneously, where the act of observation could alter the observed, and where the very fabric of reality seemed to shimmer with possibilities. This shift in perspective from the deterministic to the probabilistic had profound implications for our understanding of the universe and our place within it. No longer could we view the cosmos as a giant clockwork mechanism, predictable and predetermined. Instead, quantum mechanics presented a universe brimming with possibilities, where chance and uncertainty played fundamental roles, and where the act of observation itself became intertwined with the nature of reality. This new understanding of the universe as fundamentally uncertain, far from diminishing the power of scientific inquiry, opened up new avenues of exploration leading to breakthroughs in fields ranging from particle physics to cosmology. The development of quantum mechanics marked a turning point in our understanding of the universe, paving the way for a deeper exploration of the mysteries of existence, including the enigmatic question of the universe's origin. One of the most intriguing aspects of quantum mechanics is quantum fluctuations, profoundly impacting our understanding of the vacuum and the universe's origins. The vacuum of space is a seething sea of virtual particles, constantly popping in and out of existence. These virtual particles are not directly observable, but their effects can be measured. They borrow energy from the vacuum, only to disappear back into the quantum foam. This dance of creation and annihilation is due to the Heisenberg uncertainty principle. The uncertainty allows for the spontaneous creation of virtual particle-antiparticle pairs. These fluctuations have real, measurable effects. The Casimir effect is one such measurable phenomenon. Some physicists speculate the universe might have originated from a quantum fluctuation. At the heart of quantum mechanics lies the Heisenberg uncertainty principle. Formulated by Werner Heisenberg in 1927, it states that certain pairs of physical properties cannot both be known with perfect accuracy. The more precisely one property is measured, the less precisely the other can be known. This reflects a fundamental property of nature at the quantum level. Observation itself introduces a disturbance, making absolute certainty impossible. Position and momentum are well-known examples of complementary variables. The more accurately we know a particle's position, the less accurately we can know its momentum. This principle has profound implications for our understanding of the subatomic world. It also applies to energy and time. The more precisely we measure energy, the less precisely we can know the time interval. This leads to virtual particles popping in and out of existence. The Heisenberg uncertainty principle shapes our understanding of the quantum world. It reminds us that the universe is a realm of possibilities where chance and uncertainty play integral roles. Section 4, Quantum Tunneling, Escaping the Confines of Classical Physics. Imagine a ball rolling up a hill. Classical physics dictates it will roll back down if it lacks energy. In quantum physics, particles can tunnel through barriers. This allows particles to pass through barriers without enough classical energy. Quantum tunneling is essential for nuclear fusion in stars. It also enables atomic-level imaging and scanning tunneling microscopes. Some theories suggest it helped the universe emerge from nothingness. Quantum tunneling shows the stark differences between classical and quantum worlds. Section 5. The quantum vacuum, a seething sea of potential. The vacuum of space, often envisioned as a vast emptiness, takes on a whole new meaning in the context of quantum mechanics. Far from being a passive, inert void, the quantum vacuum emerges as a dynamic and energetic realm, a seething sea of potential where particles can spontaneously emerge and disappear. This dynamism arises from the Heisenberg uncertainty principle, which allows for fluctuations in the energy of the vacuum over very short time intervals. These fluctuations, known as vacuum fluctuations, manifest as the spontaneous creation and annihilation of virtual particle-antiparticle pairs, constantly popping in and out of existence. These virtual particles, though fleeting, are not mere theoretical constructs. They have real and measurable effects, as evidenced by phenomena like the Casimir effect, where the pressure of virtual particles outside two closely spaced conducting plates is greater than the pressure between them, resulting in an attractive force. The quantum vacuum is not merely a backdrop for particle interactions, but rather an active participant in the quantum world. It's a reservoir of potential energy, a wellspring from which particles can emerge and to which they can return. This dynamism has profound implications for our understanding of the universe, particularly its origins. Some cosmological models propose that the universe itself arose from a quantum fluctuation, a spontaneous emergence of energy and space-time from the vacuum. While speculative, these models highlight the potential role of the quantum vacuum as the ultimate source of everything we observe in the cosmos, a testament to the profound implications of quantum mechanics for our understanding of the universe. Section 6. The Hartle-Hawking No-Boundary Proposal, a universe without a beginning. The question of what came before the Big Bang, what caused the universe to spring into existence, has puzzled cosmologists and philosophers for centuries. The Hartle-Hawking No-Boundary Proposal, developed by physicists James Hartle and Stephen Hawking, offers a radical and elegant solution to this conundrum, suggesting that the universe, in a quantum sense, might have had no beginning at all. This proposal, rooted in quantum cosmology, seeks to describe the universe in its earliest moments, where classical notions of space and time break down and quantum effects dominate. Hartle and Hawking proposed that just as the Earth has no edge, no point where one falls off, the universe might have no boundary in space-time. Their proposal suggests that in the very early universe, time lost its usual meaning, becoming more like a spatial dimension. Imagine the universe shrinking down to a tiny size, approaching the Planck scale, where quantum gravity reigns supreme. At this point, the distinction between space and time blurs, and the universe, instead of having a definite beginning point, resembles a smooth, self-contained entity without edges or boundaries. The no-boundary proposal, while mathematically elegant, remains speculative and difficult to test experimentally. However, it offers a compelling alternative to the traditional picture of the Big Bang as a singularity, a point of infinite density and temperature where the known laws of physics break down. Instead, the Hartle-Hawking proposal suggests a universe that emerges smoothly from a quantum state, a universe without a beginning or an end, a self-contained entity governed by the laws of quantum gravity. Quantum cosmology applies quantum mechanics to the universe, exploring its origin and evolution. It merges quantum mechanics with general relativity, tackling the problem of time and quantizing the universe. Despite challenges, it offers insights into the universe's deepest secrets. As Section 8, the limits of knowledge and the allure of the unknown. The quest to understand the universe's origins takes us to the very edge of human knowledge. As we delve deeper into quantum mechanics and cosmology, we confront the profound limitations of our understanding. Our theories break down at extreme energies and densities, specifically at the Planck scale. We lack a unified theory merging quantum mechanics with general relativity. The nature of nothingness remains a topic of debate. The quest to understand the universe's origins is a testament to human curiosity. The pursuit of knowledge is about embracing the unknown and continuing to ask questions that push our understanding. The allure of the unknown drives us to explore new frontiers. While we may never fully unravel the universe's mysteries, the journey enriches our understanding. The universe, with its vastness and mysteries, reminds us of the limits of our knowledge. The allure of the multiverse. Beyond the familiar universe, the vastness of the universe, with its billions of galaxies, sparks wonder and awe. What if our universe is just one of many, each with unique properties? This concept, known as the multiverse, captivates physicists and cosmologists. The multiverse arises from various theoretical frameworks. Some models suggest our universe is one bubble in a vast cosmic foam. Other models emerge from string theory, proposing tiny, vibrating strings. These hidden universes might have different dimensions and forces. The The multiverse remains speculative and challenging to verify. It offers a glimpse into boundless possibilities beyond our observable universe. Section 2. Eternal Recurrence: Exploring Cyclic Models of the Universe. The Big Bang Theory has long been the dominant cosmological model. But what if the Big Bang wasn't the beginning, but one stage in an eternal cycle? This concept, known as the cyclic universe, has been explored for centuries. Cyclic models propose periods of expansion, followed by periods of contraction, leading to a big crunch. This could trigger another Big Bang, leading to a new cycle of expansion and contraction. This process could repeat indefinitely with no true beginning or end. Imagine a hologram, a two-dimensional surface that can project a three-dimensional image. Now imagine the entire universe as a kind of hologram. This concept, known as the holographic principle, challenges our notions of space and reality. It emerged from studies of black holes, where information content is proportional to the surface area of the event horizon. This suggests that the universe might be a holographic projection of information. The holographic principle has profound implications for our understanding of reality. Section 4. The Simulation Hypothesis: Living in a Simulated Cosmos. What if our reality is a sophisticated computer simulation created by a more advanced civilization? This idea, known as the simulation hypothesis, has gained traction in recent years. It raises profound philosophical and scientific questions. If we are living in a simulation, what is the nature of the real world outside? Who are our simulators? And what are their motivations? Could we ever break free from the simulation and experience the real world? Section 5. The Limits of Speculation: Navigating the Boundary Between Science and Metaphysics. The quest to understand the universe's origins often leads us to the very edge of human knowledge, where established scientific theories give way to speculation, philosophical inquiry, and the limits of our current understanding. While speculation plays a crucial role in pushing the boundaries of science, it's essential to navigate the boundary between testable hypotheses and untestable metaphysical claims. Science, at its core, relies on empirical evidence, testable predictions, and the principle of falsifiability. A scientific theory, to be considered valid, must make predictions that can be tested through observations or experiments. If these predictions are not borne out by evidence, the theory must be modified or discarded. Metaphysics, on the other hand, explores questions beyond the realm of empirical verification. It grapples with concepts like the nature of reality, the existence of a creator, or the meaning of existence itself. While metaphysical inquiries can enrich our understanding of the universe and our place within it, they are not subject to the same rigorous standards of falsifiability as scientific theories. Speculative cosmological models such as the multiverse, cyclic universes, or the simulation hypothesis often straddle this boundary between science and metaphysics. While these models might emerge from established scientific frameworks, they often make predictions that are currently beyond our technological capabilities to test. It's crucial to approach these speculative models with a healthy dose of skepticism and intellectual humility. While they can inspire new avenues of research and expand our imagination, we must be careful not to mistake speculation for established scientific fact. The history of science is replete with examples of once popular theories that were later overturned by new evidence. Embracing the unknown and the quest for understanding. The quest to understand the universe's origins takes us to the edge of human knowledge, where some questions may forever remain unanswered. Despite remarkable strides, the ultimate origin of the universe remains a mystery. The nature of nothingness challenges our understanding of reality. How can something arise from nothing? What does it mean for there to be nothing? These questions challenge physicists and cosmologists today. The quest to understand the universe's origins is a testament to human curiosity, The universe invites us to explore and question, embrace the unknown, acknowledging some questions may never have answers. The journey itself enriches our appreciation of the cosmos. The universe reminds us we are part of something greater, a cosmic tapestry woven from time, space, matter, and energy. As we conclude our exploration of the universe's origins, from quantum cosmology to the multiverse, we stand at the precipice of human knowledge, humbled by the vastness of what remains unknown. Despite remarkable progress, the ultimate origin of the universe remains a mystery. The Big Bang Theory leaves us with more questions than answers. What is the nature of dark matter and dark energy? These questions beckon us towards new frontiers. The future of cosmology promises exciting discoveries. New telescopes will peer deeper into the cosmos, capturing the universe's earliest light. These observations will refine our models of the early universe. Theoretical advances like string theory and loop quantum gravity may unify our understanding of the universe's fundamental forces. The quest to understand the universe's origins is not merely a scientific endeavor, but also a deeply human one. It is a testament to our innate curiosity and our desire to make sense of our place in the grand scheme of existence. This quest intertwines science, philosophy, and the human spirit in a tapestry of exploration and reflection. The story of the universe's origins is not merely an abstract tale of cosmic evolution, but a deeply personal one. It is the story of our own origins, the story of the very atoms that make up our bodies, forged in the fiery crucibles of stars that lived and died billions of years ago. We are, in a very real sense, children of the cosmos, our existence inextricably linked to the grand narrative of the universe's evolution. Understanding our cosmic origins allows us to appreciate our place in the grand scheme of existence. It reminds us that we are part of something much greater than ourselves, a vast and ancient universe teeming with possibilities. This realization can foster a sense of humility, interconnectedness, and responsibility towards our planet and the life it sustains. Moreover, understanding our cosmic origins can inspire us to push the boundaries of human knowledge and exploration. The same drive that led our ancestors to explore new lands and navigate uncharted seas now compels us to explore the cosmos, seeking to unravel its mysteries and unlock its secrets. This quest for knowledge and understanding is a testament to the indomitable human spirit, our relentless pursuit of truth, and our desire to comprehend the universe we inhabit. The significance of our cosmic origins extends beyond the realm of science and philosophy, influencing our art, literature, and culture. From ancient myths and creation stories to modern science fiction and space exploration, the universe has served as a source of inspiration and wonder, shaping our creativity and expanding our imaginations. In the end, the quest to understand the universe's origins is a journey without a final destination. It is a journey driven by our innate curiosity, our desire to make sense of the world around us, and our yearning to connect with something greater than ourselves. As we continue to explore the cosmos, we must embrace the unknown, acknowledging that some questions may never have definitive answers. The universe, with its vastness, its complexity, and its enduring mysteries, stands as a constant reminder of the limits of our knowledge and the infinite possibilities that lie beyond the horizon of the known. It is a universe of wonder, a cosmic tapestry woven from the threads of time, space, matter, and energy, a universe that continues to inspire awe and ignite our imaginations. The quest to understand our cosmic origins is a journey that belongs to all of us. It is a journey that transcends cultural and disciplinary boundaries, uniting us in a shared pursuit of knowledge, understanding, and a deeper appreciation for the universe we call home. As we venture further into the cosmos, let us carry with us a sense of wonder, humility, and a profound respect for the universe and the mysteries it holds. Let us never lose our sense of awe, our thirst for knowledge, and our desire to explore the unknown. For it is in the pursuit of these endeavors that we truly connect with the universe and our place within it, embracing the wonders of the cosmos and the enduring mystery of our existence.